Okay, today we're going to talk about position vectors. What is a position vector? A position vector is a vector that allows you to locate a point with respect to another point. Like in this case that you see here on the screen, you have 2 points A and B. A position vector, which is usually called with the letter R, position vector R sub AB will be the vector that is going to tell us the position of point B with respect to point A. So I'm going to draw it here. Position vector RAB will be this vector right here. This is the vector RAB. So if in this case we have point A, which coordinates, let's call it XA, YA, ZA, and point B with coordinates XB, YB, and ZB. And let's say the position vector RAB is going to be given by its rectangular components. Let's call them X, Y, and Z. Let's see how we can obtain the position vector from A to B. As we said, the position vector is a vector that locates locates a point with respect to another point. In the same way as we do here the position vector of B with respect to A, we can do the position vector of A with respect to the origin. That will be this vector here, this green vector. That vector, usually when we do a position vector of a point with respect to the origin, we only give one subindex. In this case will be RA. And it will be the vector that takes us from the origin to the point A. In order to go from the origin to the point A, we have to move this amount in the X direction, this amount in the Y direction, and this amount in the Z direction. So it's basically a vector which components are the coordinates of point A. So RA will be equal to XA I plus YA J plus ZA K. In the same way, we can define here the position vector of point B with respect to the origin. This blue vector here, this will be RB here, and the components of the vector RB will be the coordinates given by the coordinates of point B. So in order to go from the origin to the point B, we have to move this amount in the X direction, this amount in the Y direction, and this amount in the Z direction, which are the coordinates of point B. Let's draw these rectangles here, these figures here that give us a better sense of the location of the location of those vectors. I want wonder if you can see it. So you have the vector A, the vector RA, position vector of A with respect to the origin, RB, position vector of B with respect to the origin, which coordinates are gonna be XBI plus YBJ plus CBK. In this construction here, you can see a triangle here of three vectors, where by the definition of the method of the triangle to make some addition of vectors, we can recognize here that RA plus RAB are equals to RB. Let me put it in writing here. RB is equal to RA plus RAB. If you recognize the method of the triangle, that you put one vector and then next to at the end of the first vector you put the second vector, and then the resultant of those two vectors is the vector that you obtain from the tail of the first vector to the head of the second vector. So in this case, RB is equal to RA plus RAB. In this way, we can now solve for RAB, and RAB will be equal to RB minus RA. And if we express those in terms of their components, RB is equal to XB times I plus YB times J plus CB times K minus RB, that will be XAI plus YAI plus CAK. This is a B. So we have here that RAB is equal to, if we group terms with the same vector, we can group XB minus XA times I plus YB minus YA times J plus CB minus CA times K. So this is telling us that the rectangular components of the vector of B with respect to A are given, but the difference between the coordinates of the 2 points. These are the coordinates of the 2 points. And that's how you can find the position vector of a point with respect to another point. You just get the coordinates of the 2 points and subtracting axis by axis, and then that's how you get this position vector of one point with respect to another point. So let's take a look at this example here. Let's say that the coordinates here of A are, say, in X we have 4, and Y we have, let's say, 1, 1 here, and in the C direction, sorry, let's put 2. X, Y, C. In the Y, for the point B, let's say the coordinates are X equals to minus, let's say minus 2. Let's say this is minus 2. In the y direction, let's say 1, 2, 3, 4, 5, 6. In the z direction, let's say this is 2. So let's say the coordinates here are xa 4, ya 1, z minus 2. So we have to do the subtraction of the coordinates of the point. So let's put here point B minus 2, comma 6, comma 2, and A equals 4, 1, minus 2. So we do the subtraction of this. So we have here minus 2 minus 4. Here we have 6 minus 1. And here we have 2 minus 2. So we have minus the vector from A to B will be minus 6i plus 5j plus 4k. Let's put it here. Like this. So that will be the vector, the red vector from A to B. And that's how you obtain it. So we want to make a graph of this. Let me clean this up a little bit. We're gonna make this we're saying that in order to draw the coordinates of the position vector of B or with respect to A, let's put it here, you have to move minus 6 in the x direction. So that will be something like 1, 2, 3, 4, 5, 6 plus 5 in the y direction. 1, 2, 3, 4, 5 and plus 4 in the z direction. 2, 2. So that's how you go from A to B, and that's how the coordinates or the components better of the position vector of B with respect to A. Let me do this complete let's complete the rectangle here so it looks nicer. So here we have 4, here we have 6, then we have this like this, we have this like this, this is also 6. Okay, so I hope you can look at it and let me remove these coordinates now. And you should be able to see it. That's the position vector of point B with respect to A. All right. This is a very important concept that we will be using a lot. And in our case, we are going to use it in order to find the components of a force in the direction of a given line. So we already did something like this without saying that was position vectors, but that was kind of what we were doing in the last class in a couple of examples that we did right there. But now we have like a more formal way of doing. Basically, what is you have to do is organize the coordinates of the points, and you subtract, in this case, B minus A. So if you're going from A to B, you subtract B, you subtract A, subtract the coordinates of point A A from the coordinates of point B, and those are the magnitudes of the rectangular components of the position vector. So let's make an example about this. Okay, so here we have an elastic rubber band that is attached to points A and B as shown. Determine its length and its direction measured from A toward B. So basically what they are asking here is to find the position vector of B with respect to A. That will be a vector that goes like this. So if we find this vector, if we get the length of the vector and the angles that this vector makes with respect to the axis, that will be the answer to this problem. So what we need to find here is we have to find the coordinates of the points and then make the subtraction, and that's basically the components of the rectangular components of the position vector. So point B, x in the x direction, here is the x-axis. So point B has -2. In the y direction, this is the y direction. So the distance from the origin to in the y direction will be this distance, 2 meters here. And in the z direction, 3. So those will be the coordinates of point B. Now coordinates of point A. In the x direction, point A, 1 meter. In the y direction, this point is like on the plane xz, so 0. And in the z direction is going -3. Alright, so you just make the subtraction of this. So this subtraction here will be -2 minus 1. This subtraction here will be 2 minus 0. And this subtraction here will be 3 minus 3. So this is -3, 2, 6. So the position vector of B with respect to A, so RAB is equal to -3I plus 2J plus 6K. So what we have here is the rectangular components of the rubber band, or the vector from A to B, which has -3 in the x direction. So we have -3 here, 1, 2, 3, something like this, plus 2 in the y direction, something like 1, 2, and plus 6 in the z direction. So it will be something like this, and then we get to the B point. Let me put that one a little better here. Okay. So this will be -3 to 6. That's how you go from A to B. Let's take a look at this like in a separate picture so we see more clearly. Okay, so here we have it. So this is -3 I to J 6K. All right. Now, if we want to get the length of the rubber band, that will be the length or the magnitude of the position vector. So we can calculate this as, by the Pythagorean theorem, RB magnitude will be equal to the square root of minus 3 square plus 2 square plus 6 square. This comes to be 7, equals to 7. So that's the magnitude of the vector. Now if we want to get the direction of the vector, those will be the angles that the vector makes with respect to the coordinate axis. So basically we need to get the cosines, and then we get the arc cosines, the direction cosine. So with the arc cosine of these values we get the angles. So cosine of alpha will be minus 3 divided by 7. Cosine of beta will be 2 divided by 7, and cosine of gamma will be 6 divided by 7. So from here, alpha, we get the arc cosine minus 3 over 7, we get 115 degrees. From here, beta, arc cosine of 2 over 7, we get 73.4 degrees, and gamma, we get 31.0 degrees. I want to see that in a graph. It will look something like this. Here it will be, make a copy here. So if we want to see the angles here, will be a little bit, have to be very careful to draw this. Then we have alpha, the angle that the vector makes with the x-axis. So that will be this angle here. This will be alpha. Beta will be the angle that the vector or the rubber band makes with the y-axis. That will be this angle here. And gamma will be the angle that the vector makes, or the rubber band makes, with the z direction. And that will be it. Maybe it's important to point out that all these angles are measured from the positive axis, right? From the positive axis. So this will be 115, this will be 73.4, and gamma will be 31.0 degrees. All right, that will be it.